Hello, this is the start of the 8th session, ninth session. Continue to talk about different forms of silicates. Another one is layered silicate, as you can see here in this photo, down left hand side. As it's mentioned here, the examples are in clays, mica, and talc. Here, silica tetrahedra is connected together to form a 2D plane, so they are connecting to each other and they form a 2D plane. A net negative charge is associated with each Si2O5 unit. This one here, the negative charge balanced by adjacent plane, which has positively charged cations. An example of layered silicate is kaolinite clay. It's a layered silicate mineral with one tetrahedral sheet of silica, SiO4, linked through oxygen atoms, as you can see here, this pink color, to one octahedral sheet of alumina. And the one here, the alumina, as you can see here. Bear in mind that the adjacent sheets of this type are very loosely bound to each other because they have, or there is a van der Waals force between them. Now we move to different forms of carbon. The first one is diamond. Diamond has a tetrahedral bonding. Of course, the bonds are between carbons. Diamond is the hardest material known, and it has very high thermal conductivity. There are different types of diamond. Of course, we have large single crystals like gemstone, small crystals that are used to grind or cut other minerals, and there are thin films that they can be used as hard surface coating in cutting tools and also medical devices. Another form of carbon is when they are forming a layered structure known as graphite. These layered structure, they have parallel hexagonal arrays of carbon, as you can see in the picture. These hexagonal arrays are parallel to each other. Again, similar to the case of kaolinites, they have weak van der Waals forces between them. So the straight lines here represent van der Waals force. Here planes actually slide easily over one another. That's why these materials are very good lubricants and used for lubrications. Regarding crystallinity in polymers, we'll talk about it in polymer chapter 5. Crystals are not always very small. They can be also as building blocks. Some engineering application it requires single crystals. As an example, turbine blades. Why do we need a single crystal in turbine blade? When temperature of turbine blade under high stress is raised to a critical point, the creep rate quickly increases. A single crystal structure has the ability to withstand creep at higher temperature than crystalline turbine blades. This is due to the lack of grain boundaries in single crystal, so it's very desired to use single crystals in turbine blades. We can also see another example in using crystals for abrasive, as you can see here in this picture. Some properties of crystalline materials can be related to crystal structure. An example is quartz, as you can see here. quartz fracture usually easily along some crystal plane than others. So you see this kind of sharp planes after fracture of quartz. Bear in mind that most engineering most engineering materials are polycrystals, so they have different crystals. This picture shows an example of niobium hafnium tungsten plate with an electron beam weld. This has been polished and etched and is observed under the microscope, and you can see different grains. Each of these colors are showing a grain, and some of them are towards certain direction and some of them are equally distributed. Each grain here is a single crystal, and if grains are randomly oriented like here, overall components properties are not directional. Yeah, let me correct it. If grains are randomly oriented like these ones, then the properties are not directional. We call it isotropic material. Of course, if they have a certain orientation, then the material is anisotropic. This material, this plate is anisotropic in this part and isotropic in these regions. Grain sizes typically range from 1 nanometer to 2 centimeter, as shown here. And it's a 2 centimeter, it means that we have millions of atomic layers there, and of course for those are just nanometer, we have very few number of atoms in each grain. In comparing single versus polycrystals, single crystals and polycrystals, in single crystals properties vary with direction, so they are generally anisotropic. Examples are the modulus of elasticity in, as an example, BCC ion. For polycrystals, properties may or may not vary with direction. If grains are randomly oriented, like here, as you can see, we have isotropic material. As an example, the Young's modulus for a polycrystalline ion is 210 gigapascal. And if grains are textured, as you can see here, they have a certain direction oriented along horizontal line. This is anisotropic, and materials behavior around or along this line, of course, is different with what you have along this orientation. Yeah, in case we have two or more distinct crystal structure for the same material, this is called polymorphism. We have different morphology or shape of the material. Examples are shown here: titanium, alpha, beta. For carbon, for diamond and graphite, they have their certain. Each of them has a certain distinct crystal structure. Another example is ion system, in which different phases or different forms, alpha, gamma, and delta, have different crystal structure. As you can see, BCC, FCC, VCC, and their melting temperature is different. Now we move to find another property, which is linear density inside the unit cell. The linear density is actually the number of atoms along a line divided by unit length of the direction vector. So the length of we take the length of the vector into consideration, and then we take the number of atoms in that direction into consideration, and then we divide them by each other, and that's the linear density. Example is here shown for aluminum, based on the tables, including the very first table, the first page of the book. Aluminum has FCC crystal structure. If you want to find the linear density along 110, you know this direction is 110. Of course, from book we can find the atomic radius of aluminum to be equal to 0.143 nanometer. And because there is a relation of root of 2a, a is the side of the unit cell, is equal to 4r, this side is equal to 4r, then from radius we can find the value of a equal to 0.405 nanometer. The linear density is the number of atoms. Of course, in this line we have 1 in the corners and 1 in the center, so 2 atoms divided by this length, which is the root of 2a. We have an result in this relation for linear density. A similar definition can be made for planar density, as shown here. So what we do here again, we look at the 2D plane or a 2D view of the unit cell. We find the number of atoms in that 2D view and then divide it by the area of the unit cell. Of course, for cubic crystal structure, we end up with planar of square or rectangular shape, and we know the value of A for each side. If we know the value of R, we can find the value of A using this relation for BCC or different relation for FCC. If you want to find the planar density along this plane, 1, 0, 0 plane for iron, you know 1, 0, 0 plane is passing from x-axis, so this plane in the front can be 1, 0, 0. The number of atoms are, of course, we have 1 over 4 times 4, so 1 atom. And the area is a to the power of 2, as you can see here. We have this relation for R. The radius of iron based on the table is 0.124 nanometer. So if you plug this value into this relation and use it here, we find the value of planar density of iron along 1, 0, 0 plane. Now let's look at another example. This one needs that you work it out for you. Here we want to find the planar density of iron in 1, 1 plane. You know 1, 1 plane is a plane that's passing or intersecting with x, y, and z axis at 1 unit, as shown here in these triangular planes. So what we do, we try to look perpendicular to these planes or these triangular planes, as you can see here. Then we have to find the number of atoms in each plane and divide it by its area in order to find its planar density. As you know, if each side of the cubic unit cell is A, of course this size is root of 2A, because later we need to find the area of this parallelogram, which is equal to area of 2 triangle. We have to have the value of h, the height from this point to this point. Using Pythagoras theorem, we can find these values. Let's work it out further and complete the answer to this, or solution to this question in the class. Okay, so far we talked about different crystal structure, how atoms are spaced in a crystal structure, but how we can exactly determine this and characterize this and look deeply into the crystal structure, how we can get close and see the spacing between atoms. This is the basis of X-ray diffraction. If you look at different spectrum, the electromagnetic spectrum of different type of waves, you can see based on the frequency, we have different range from very low frequency waves to very high frequency, and the value of wavelength, which is the distance between the corresponding points in each wave, is starting from very low value to very high value, as 1 meter for long radio waves. If you look at this range, we have infrared, and this range here ultraviolet, the same. And when you look at X-ray, you see X-ray is the length, or the wavelength is in the range of 1 nanometer. And if you remember, the size of atoms are close to this size. So if we use X-ray, we are able to go deep into the atomic structure and find more information about the material, or each material or crystal that we are studying. Diffraction starts when a wave encounters a series of regularly spaced obstacles that are capable of scattering the wave and have spacing which is close to the wavelength. Because this spacing between atoms, as shown here, is close to the wavelength of X-ray, So we can use X-ray if you assume two X-rays are going and one of them is reflected by this layer similar to ray number 1, and the other ray, like ray number 2, going to the second layer and then reflected. And if we can detect these two, and if these two waves has or have the same, or are parallel or synchron, or are in the same position in their wave, then we can detect it. Then we will be able to relate the value of spacing between planes shown by D here to the value of lambda, which is the wavelength of our ray, which is X-ray here. If we do the calculation, we see the distance, the extra distance that's traveled by X-ray number 2 is this pink path, as you can see here. And if we do simple trigonometry here, we can relate these paths to D using this relation. Of course, if these two rays are detected by detector, the extra path should be integer multiplication of the lambda, or the wavelength of the ray. So we can end up to this relation, as you can see here. So if we have the angle of ray theta, we can then calculate the value of the, or in general, if we have the wavelength, if we have the theta, which is the angle of ray attacking to the crystal, then we can find the distance between atom. This is the basis of X-ray diffraction crystallography. Bear in mind that the chance of this diffraction is more when we have more condensed layer, or when the ray is attacking to a more condensed layer of atoms. So if we see a large value of diffraction, so we expect that from that point we have a condensed plane. Same point is used here. So if we look at the diffraction pattern for polycrystalline alpha ion, which has BCC crystal, we can see we have a higher value of intensity in these 3 points. The first one happens in angle of almost 22 degree, because this is 2 theta 45, so angle of 22 degree, which results in this plane. The second one is an angle of almost 35 degree 33 degree, which represents this plane, and the last one represents plane 211. So here the high intensity peaks result when the diffraction condition, the Bragg diffraction condition, is satisfied by some set of crystallographic planes. These peaks are shown here in the form of this Miller indices. This is the last slide. In summary, we talked about common metallic crystal structure like FCC, BCC, and ACP. We talked about items like coordination number and atomic packing factor. We talked about how to predict the density in terms of atomic weight, if we have atomic weight, atomic radius, and crystal geometry. We talked about interatomic bonding in ceramic, which is either ionic or covalent. We talked about the ceramic crystal structure that is based on charge neutrality and ratio of cation to anion radii. We also talk about the fact that some materials can have more than one crystal structure. This is referred to as polymorphism or allotropy. And at the end, we talked about the fact that we can use X-ray diffraction for crystal structure and to find and determine interplanar spacing. Thank you very much.